Hey guys, I hope you're having a good day. I just wanted to go through these notes. I really couldn't find a video that did a good job going through the introduction to thermochemistry for what we have to teach you. So thought I'd just make one. But talk about thermo energy. Thermo is heat. So we are talking about energy when we talk about thermochem. And so if you're interested in the type of energy that we talk about or are interested in learning in other types of energy, you should take physics. There's a huge unit on that, and it's a lot of fun. So if you like this, then that might be something you want to look into. So when we talk about thermal energy, we're talking about the study of the heat changes that occur. Now, it's in a chemical reaction. That's pretty easy. We'll look at some examples. You learned about all kinds of chemical equations and reactions a couple units ago. But then there's also phase changes. So phase changes is when we're going like from a solid to a liquid or a gas to a liquid or vapor to a liquid. So gas and vapor can sort of kind of be used interchangeably. If it's a gas, then it's a gas at room temperature. If it's a vapor, that means it's not a gas at room temperature. And so you had to do something to it to make it a gas. You had to heat it up. Energy is technically just your ability to do work or produce heat. And your unit for energy is going to be a joule, and that's Joule. And so that's abbreviation is a J for that. So anytime you are calculating energy, if you see a question that asks you to calculate energy, your unit at the end of your numerical answer should be a J, which represents joules. All right, two forms of energy, potential energy and kinetic energy. Potential energy is possible energy. That's the best way I can think of. I could put a technical fancy definition, but all it really means is I have a potential of having energy to do work. That's what potential energy is. Now, there's tons of types of potential energies. We aren't going to talk about all of them because it's not relevant. Again, if you're interested in that, that's a physics topic. Take physics. So, example I put here is a ball sitting at the top of a hill has potential energy. That potential energy would be in the form of gravity. So, if the ball rolls off the hill, you now consider, oh yeah, it has energy because it's moving. But we can't just make energy. It's kind of like the law of conservation of matter. We can't just make matter. It's not just like poof. We have to define it as coming from somewhere and moving to somewhere else. That's the transfer of energy. So it's kind of like the change in matter when you're making a recipe for a cake. You start out with your ingredients, you put it together, and you make a cake. So that can be one type of potential energy. We'll talk more about chemical potential energy because that's what's relevant to this course. You also have kinetic energy, and kinetic energy is energy of motion. So the ball rolling down the hill would be kinetic energy. Or if we talk about changing types of energy, you eat a cheeseburger. When the cheeseburger is sitting in front of you, it's potential energy. It's a possibility of having energy. But once you eat it, it turns into it can turn into kinetic energy or other forms of energy, such as heat also. So those are just some examples where you can go between the two different types of energy. Again, underneath each of these, especially your potential energy, you have sub energies that go underneath here. And again, if you want to learn more about those, that's a physics thing. So let's look at chemical potential energy. It's the energy that's stored in a substance because of its composition. So we're talking about what it's made up of. And the stronger your bonds are in whatever substance you're talking about, whatever compound you're talking about, the stronger your bonds, the more potential energy you have. Now, we talked about strength of bonds back couple units ago when we did the unit on bonds, and we talked about single, double, and triple bonds. We talked about triple bonds being stronger than your single bonds, and so you have to break or pull apart 6 electrons on a triple bond versus a single bond, which you only have to pull apart 2. So your chemical energy in that is much higher. If you get the flex fuel, for example, if your car runs on flex fuel versus getting regular unleaded gas, then your flex fuel actually, the bonds are broken easier in the solution that makes up the flex fuel. You don't get as good of mileage on your flex fuel as you do on regular gas. Now, I've done the math. It's actually still cheaper to buy the flex fuel, even though your miles per gallon is going to be less. But that's why you get less gas mileage, because the bonds that are being broken aren't as strong. All right, let's look at heat. So your heat's a form of energy that always flows from warmer objects or surroundings, whatever, to colder or cooler surroundings or objects. So we go from hot to cold, high to low, more to less. Okay, that's everything we're talking about, from weather to movement of electrons to make a battery work. Okay, it's always going to go from more to less. That more could be electrons, it could be heat in this example. But that rule doesn't change no matter what you're talking about. Your energy is going to go from high to low. So your symbol for energy, symbol for heat, not energy, is Q, and we measure it as a calorie. And a calorie is the amount of heat required to raise 1 gram of pure water. So we're not talking about water out of your faucet. That's not pure water. So 1 gram of pure water by 1 degree Celsius. Please don't use Fahrenheit. So we have to use Celsius. Just a little bit of here, we could have to do some calculations between calorie and kilocalorie, just to remind you that kilo is 1,000, so 1 kilocalorie is 1,000 calories. 1 joule is 0.2390 calories, and 1 calorie is 4.184 joules. This last one is the one we use the most. If you have to do like a conversion between calories and joules, you see the 4.184 a lot. People don't like decimals, so they don't like this one as much. Okay, you can use whichever one you please, whatever makes you happy and floats your boat. I don't care. But most people don't like decimals, so they use this one down here, the 4.184, and I do believe that's on your reference guide. But this is just dimensional analysis. This is just being okay with being given one unit and having to figure out how to get to another one, which we've done. All right, temperature is a measure of average kinetic energy here. So that should be kinetic energy. Now let's talk about different types of reactions. So we have endothermic and exothermic reactions here. So endo means in, so a reaction that requires heat to occur. They absorb heat. A good example here is, you're going to laugh, but like a whipped cream can, when you shake a whipped cream can, you're putting energy into that system. And to turn it into the whipped cream requires energy. So the outside of the can actually feels cold. Exothermic reactions are ones that produce heat. An example of that is a hand warmer. So when you go to a football game and it's really cold and you take your hand warmers, you actually break 2 different parts in the hand warmer, and those compounds start to react. When they react, they produce heat. Okay, that's an exothermic reaction. A calorimeter is a system where you have different substances that are transferring heat between each one. No heat is gained or lost. And this is a closed system. A closed system is just one where you've got a top on it. Think of putting a lid on a pot. So that would be a closed system. Sonar calorimeter, I don't know that I answered that one. An insulated device used to measure the release or absorption of heat in a chemical or physical change. And then down here, for a closed system, no heat is lost or gained. So you have to remember that. So no heat is lost or gained within that actual system. So it may be transferred from one substance to another. So think of all the cooking shows that you watch where you have to temper your egg. So you can't pour a hot liquid into the egg. If you do, it will scramble the eggs. That's because heat is transferred from the hot liquid to the eggs and will cook the eggs. So you have to temper your eggs. All right, specific heat. That's the heat that's needed to raise the temperature of 1 gram of substance by 1 degree Celsius. So we talked about that sort of up here with a calorie when we talked about water. But now we're going to define specific heat as any substance. So it's not just water. So on page 1 of your reference guide, you'll find a chart that has tons of specific heats on it for different substances. And that's what you'll use to do your calculations. So here you have Q is your heat transferred. C is your specific heat. That's found on page 1. M is going to be your mass. So we're talking about grams here. We're not looking at moles. So don't confuse that. You don't need to change to moles here. We're talking about mass. And then T is your temperature. So your temperature, we're looking at a change in temperature. So we're looking at final temperature minus initial temperature. So there's a couple of examples here. I'm going to post walking through these examples for you, but I don't have enough time on this video to do them. So they're here. We will do them. If you want to go ahead and try them, that's great. They're simple to do. Just use this reaction here, or this equation, sorry. But I wanted to look one last place at law of conservation of energy. So energy cannot be created or destroyed. It just goes from one form to another. So we have kinetic energy, we have potential energy. Under your potential energies, you have lots of different types of potential energies. You have different types of kinetic energies that you can talk about, even though they're all energy of motion. Different things are moving. So you can define it in different ways. But the same principle is applied no matter what type of energy you have. If you have energy that's being lost somewhere, somewhere else is gaining that exact same amount of energy. So it's useful sometimes to figure out what do I need to add to raise the energy or the temperature or the heat content of this specific substance that I have. So you're going to use the specific heat equation. If you notice here, CMT, you have C, M, and T. Okay, so you're using the same equation here. You just have it twice. So you have whatever substance here that's heat is lost, and then whatever substance here that heat is gained. Now, honestly, it doesn't matter where you put the negative. It's just got to be whatever is positive on one side has to be opposite on the other side to get your math to work out. So it depends on how you view the negative and decides where you put it. But in the grand scheme of things, it doesn't really matter. All right, for this one, you need to go through and somehow denote all the data that goes with whatever heat lost and all the data that goes with whatever heat is gained. So I would like underline everything that heat is lost and circle everything that heat is gained or something to keep those numbers straight. It's kind of like gas laws when you had your initial and then your final after things were changed. You had to keep things separate. You had to have a way to keep your two volumes separate or your two pressures separate. The same thing goes from here. It's very easy to make a mistake on these if you don't have a system to know which side each piece of data goes on. So again, if you want to underline all of the data that goes with lost and circle all the data that goes with gained, that's a great option. And I will put this on a piece of paper and post these as well But I only have 15 minutes and I got like 5 seconds left. So hope you guys have a great day.